To close this lecture, we will be discussing some of the thermodynamic aspects of passive and active transports of solutes through lipid bilayer membranes. We start here with the concept of passive transport. By passive transport, we refer to the transport of solutes in the natural direction, that is, in a direction of decreasing chemical potential or decreasing concentration, as was described in Chapter 4 when we discussed the osmotic pressure. The figure displayed on this slide shows two regions which are separated by a plasma membrane and which exhibit different concentrations in a nonpolar solute. Since this solute is not charged and does not exhibit a strong dipole moment, it can relatively easily go through the hydrophobic region of the membrane. The solute will diffuse spontaneously in the direction that decreases its chemical potential, hence in the direction of decreasing solute concentration, here from the region above the membrane to the region below the membrane. The net flow of solute will stop and equilibrium will be reached when the solute has the same chemical potential, hence exhibits the same concentration on either side of the membrane. If we can assume that the solute behaves ideally, that is, if it follows Henry's law, then the free energy change associated with the transport of solute A across the membrane from the outside of the cell into the cell can be represented by the following equation. Note that the molarity of A inside the cell is on the numerator, since this is the final state of the solute, while the molarity of A outside the cell is on the denominator, since this is the initial state of the solute. As long as the molarity of A inside the cell is less than that outside the cell, delta G for the transport process will be negative, since the argument inside the natural logarithm is less than 1. Let us now examine the transport of ions across such plasma membranes. Ions are highly hydrophilic and will not spontaneously go through the hydrophobic tail region of the membrane. Hence, their transport across the membrane must occur by a different process. One of the possible mechanisms of transport involves the use of ion channels and stimulus molecules. A stimulus molecule is a small molecule which can bind with the ion channel, typically a protein, and trigger a conformational change in the protein that allows the channel to open for a specific ion. There are specific proteins or specific channels for specific ions. Transport through ion channels is also a case of passive transport, since ions again flow in the direction of decreasing chemical potential. This kind of transport is called facilitated passive transport, since it is enabled or facilitated by the presence of ion channels and stimulus molecules. Again, this process reaches equilibrium when the chemical potential of the ionic solute is the same on both sides of the membrane. One should be aware that the chemical potential of ionic solutes is not only affected by the concentration of ions, but is also modified by the solute electrochemical potential. On the next slide, we will address this issue and discuss the concept of membrane potential.